Welcome to Unprocessed Math. In this lecture, I'm going to talk about integration by parts. So integration by parts formula tells us that the integral of fg prime is equal to fg minus integral of f prime times g. And this is basically the integrated form of the product rule of differentiation. And if you do substitution and if you take u equals f, g equals v, you can actually rewrite this in a simpler form, and this will be transformed to integral of u dv equals uv minus integral of v du. And when doing integration by parts, you're basically hoping that the integral that you want to get on the right-hand side is going to be simpler than the integral that you started with. So, and that's basically the key idea in doing integration by parts. So the difficulty in using integration by parts is in deciding which part of your integrand should be taken as u and which part should be taken as dv. And u is generally taken to be the part of your integrand which has an easier derivative, and dv is the part that has an easier integral. Let's look at this first example. Suppose we would like to integrate the function x e to the x. I'm going to take u to be equal to e to the x and the rest, which is x dx, as dv. So what I have here now is u dv. That's u and this is dv. The next step would be to compute du and v. So u is equal to e to the x. Du is going to be the derivative of e to the x, which is e to the x times dx. dv is equal to x dx. V is going to be an antiderivative for x, which is x squared over 2 using the power rule. Now, integration by parts formula tells you that this integral is going to be equal to u times v, that's what I have here, minus integral of v du. So if you multiply those two terms together, you have x squared over 2 multiplied by e to the x dx. So integration by parts formula gives you this right-hand side. And now, looking at this integral, you see that this integral actually seems to be more challenging than what we started with. And the reason is that we had the wrong choice of u. Remember, I told you that you generally want to take u to be a function that has an easier derivative and dv to be a part that has an easier integral. Now the problem here is that, so you see why this is more challenging, because instead of having x here, now I have x squared over 2, which seems more challenging. The reason that we are getting this more challenging integral is that we took dv to be equal to x dx, and the integral of x is more challenging than x. So by choosing v to be equal to x dx, we are basically replacing x with x squared over 2. That's what happened here. So what you wanted, and how about u? So I took u to be equal to e to the x. The derivative of e to the x is e to the x. So it's not easier. It's also not more difficult. So this part is fine. But the problem is that dv has an integral which is more challenging than what we started with. So what you have here is not going to work. So you had the wrong choice of u. So I'm going to try one more time. This time I'm going to take actually u to be equal to x. So I take u to be equal to this function and the rest to be dv. So this is u, and I take e to the x dx to be dv this time. So you break it up, this integral, as the integral of u dv. This is u, that's dv. Now let's repeat the same process. So u equals x, du is going to be the derivative of x, which is 1, multiplied by dx. So du will be dx. and dv is e to the x dx, so v is going to be a non-type derivative for e to the x, which is e to the x. Now, integration by parts formula tells me that this integral is going to be equal to uv, so it's going to be this times that, and that's what I have here. This is x times e to the x, that's what I have here, minus integral of v du. V is e to the x, du is dx. So it's going to be minus integral of e to the x times dx. And we get this integral. Now notice that the interval that I'm giving here is e to the x, which is simpler than what we started with. And the reason that this integral is easier is because u has an easier derivative. U equals x, the derivative of x is 1. So what we are getting here is going to be simpler. Finish off this problem. This integral that we are getting here is extremely easy. So I have x e to the x, and integral of e to the x is e to the x. And I add a constant. So the integral of x e to the x is going to be x e to the x minus e to the x plus some constant. Let's look at another example. So here, we would like to integrate the function x sine x. And I'm going to take u to be equal to x. After seeing the previous example, you know why u equals x might be a good choice, because the derivative of x is 1, and constants or 1 is much easier to deal with than compared to x. So I take u to be equal to x, that's u, and I take the rest to be dv. The next step is always to compute du here and compute v here. So du is going to be dx, and v is going to be the antiderivative of sine. Antiderivative of sine is minus cosine. I'm basically integrating sine. It is minus cosine. Now, using integration by parts formula, we know that this integral is going to be equal to uv, that's what I have here, x times minus cosine x, minus integral of v du. So I multiply those two, and that's what I have here. So this is minus integral of v du. And now you see that you can cancel these minus signs, and this will be simplified to this integral. And notice that the integral now that I'm getting in the right-hand side is easier to deal with than what we started with. And the reason that you're getting an easier integral is because the derivative of the function x is easier than this function itself. And to finish off this problem, you know that integral of cosine is sine. So I just copy the same term here. And integral of cosine is sine. And you add the constant of integration. Let's look at another example. Here, we would like to integrate the function x squared natural log of x. So here, I want to choose u to be a function which has an easier derivative. You can take u to be equal to x squared. The derivative of x squared is 2x. 2x is easier than x squared. It has smaller power. But how about taking u to be equal to natural log of x? So if I take u to be equal to natural log of x, then the derivative of natural log is 1 over x. So you see 1 over x is much simple, it's much easier to deal with than natural log of x. So that's what I'm going to do. I'm going to take u to be equal to natural log of x here, and the rest as dv. So x squared dx will be dv. The next step is to compute du here and to find an antiderivative for v here. So basically for x squared dx. Du is going to be the derivative of natural log of x, which is 1 over x, multiplied by dx. And v just becomes an antiderivative for x squared, which is x cubed divided by 3. Now I have all the computations that I need to to use integration by parts. So this integral, which is u dv, is going to be equal to uv. It's u times v. That's what I have here. So it's this function. It's this function multiplied by this function. So this is uv minus integral of v du. So you multiply those two terms together, and that's what I have here. So I have x cubed divided by 3 multiplied by 1 over x dx. This is what I have here. Now let's see what happens. We can simplify this. So I just copy the same term. Minus, you bring out 1 over 3 outside of the integral sign, and x is going to cancel x cubed, and it will simplify to x squared. And now you see the integral that I'm getting in the right-hand side is much easier than what we started with, and there's no natural log in it. The reason is that we took u to be equal to natural log of x. The derivative is 1 over x, so after differentiating u, natural log is gone. That's why you don't see the natural log here. Now this is a very easy function to integrate using the power rule. Integral of x squared is x cubed divided by 3, and everything else is the same. You simplify this, and the final answer becomes, so this simplifies to x cubed divided by 9, and you add a constant. Let's look at another example. So here I want to integrate the function natural log of x. Now after seeing the previous example, you know that u equals natural log of x is a good choice of u because its derivative is a much simpler function. It's 1 over x. So I'm going to take u to be equal to natural log of x, and the rest, which is just a dx, as dv. The next step is to compute du here, going from here to there, and then here I compute v. So du is going to be the derivative of a natural log of x, which is 1 over x multiplied by dx, and v is going to be x. Basically, dv is equal to 1 times dx, and an antiderivative for v is x. Now you can use integration by parts. This integral is going to be equal to u times v, which is, so u times v is x natural log of x minus v times d. So it's minus, this is v, that's du. So, and now you see that x's will cancel, and this integral simplifies to integral of 1, which is an extremely easy integral. So you see, after applying integration by parts, I'm replacing this integral with an integral which is much easier to deal with. Integral of 1 is x, so I replace that with x, and I add the constant of integration. For additional practice, take a look at the problems in section 6.2 of the APEX Calculus 2 textbook, and for any additional help, check out mathmaticians.com.